So coming as the last talk on a very busy day of presentations, and being the last person between you and the dinner, which I'm sure will be quite nice, I will keep it light and hopefully somewhat entertaining. This may be somewhat new information to some of you and some to not, but it's an extension of a couple of elements of work that we've been doing in Hawaii and in conjunction with some of our other collaborators. And I'll be talking about, as a lead-in, since it's a calorimeter section, I'm going to be talking about a very different kind of calorimeter than you've probably seen before. Okay. So the brief outline is the following. So I'm going to talk about a radio emission-based calorimeter based on the Ascarian effect, and I'll talk about what that is. What's nice about it is it can be very highly integrated, and it's extremely radiation hard, as I'll show you. The other advantage it has is because it's based upon Cherenkov radiation, it's very prompt, and so you can get very good timing, and I'll show beam test results that we have for this. And so, based upon this then is motivation. These are sort of motivating slides to talk about why we would want to get to the picosecond level. We're actually starting to do studies to go to the femtosecond level, but that's beyond what you probably need for this type of detector just because of spatial reasons, but I'll comment upon that briefly as well. Okay, so the place that I got involved in this, at least, was trying to build very high-energy neutrino detectors that could cover, millions of square kilometers of detection area. And so this was actually predicted already by Gergen Ascarian, the handsome devil over there, in the 1960s, which is that you could use a radio-transparent compact solid as the shower mechanism. If it's dense, the shower that gets induced it radiates at wavelengths long compared to the shower size coherently. Okay, so what he predicted specifically what would happen is you get a local relativistic net negative charge excess, so it looks like a radiating charge moving through relativistic speeds. As a result, for very high energy showers, the emitted RF power goes to the square then of the shower energy, which is very nice. And these would be predicted you'd be able to measure these at quite long distances. Moreover, you could actually figure out, even with a relatively few number of measurements, where you are, because you could measure the pointing vector to determine where you are in the Cherenkov cone. Now, of course, if you measure the entire thing inside a confined space, then you can do better than that, and that's what I'll be talking about the rest of today. Okay, so actually when we first proposed this, especially in Antarctica, people were skeptical. They said, well, maybe this really doesn't work as predicted. And so we did a number of measurements where we built a mini Antarctica at SLAC and fired the primary beam into it. You're very familiar with the blue glow from Cherenkov light. This is the radio counterpart of that. And we're able to very clearly map out and measure the emission, and it very much followed expectations from his original derivation, which have been subsequently elaborated upon, but are very solid. I mean, this is really very nice basic physics. Okay, so in order to turn this into a calorimeter, the idea then is you would take a waveguide, which you've hopefully done a very good job of matching to your readout RF electronics. You have some type of showering mechanism. Okay, you have a pre-shower in this case, but you can imagine a sandwich structure of some kind, which would be optimized depending on the energy you're targeting and so forth. And as the relativistic shower goes through these alumina-weighted loaded waveguides, it produces, of course, Cherenkov emission. Okay, this is a picture of what the inside of the cryostat looks like that has these waveguides inside of it. What's very nice about this is alumina is often used as a support material in nuclear reactors. So it's extremely radiation hard. And of course, the walls can be whatever material you want as long as they're reasonably conductive. Okay, as an example of the simulations we need to do to better understand this, we needed some tweaking in JAMP, but eventually got a good matching between the shower that developed in our detector. In this case, we have 3 detector elements that were run at the end station A. And we then feed this into a separate simulation that we do, knowing the number of charged particles in each of these waveguides with these various parameters, into a subsequent model, okay, which is based on finite time differential transforms. And so what you see here is the initial burst of the shower going through. It's about 20 picoseconds. That then expands out through the waveguide and goes through the tapering section and then gets measured. So the actual overall pulse itself has this fairly complicated shape, which we're here in simulation, and you can see the actual measurement. There's a little bit of attenuation in the higher frequency component on the reflection due to somewhat less than ideal matching. But this very complicated thing, looks very messy at this point, the direct and the reflected. But once you deconvolve this, you get a very nice sub-picosecond, well, the actual shower itself could be resolved sub-picosecond, but we resolve it at the few picoseconds levels I'll show you once you deconvolve it. Okay. So just to show how it behaves in a coarse sense, this is the measured then peak voltage field that we see out the output of our low noise amplifiers as a function of the bunch charge that's injected in. One of the problems, of course, unless you really run this cold or do a better job with the amplifiers, is that we're relatively turning on at fairly high shower energies. That's a known feature of this, so this would work very well in very forward directions with extremely high radiation, but is not probably what you would want for your electromagnetic calorimeter, for instance. It's just too high energy, unless you could talk about a real future collider. But you can see you get a nice dependence here, and the energy scale is not terrible. Okay. Now, one of the real selling points, and this is what's leading to me to talk about the ASICs themselves, is how you can do in terms of the timing. Okay, so you see as you go higher and higher in shower energy, okay, as you shower it up here, you're getting much, you can see graphically you're getting much more tight timing that you get out of this. So this then shows the subsequent transit through the different layers of our 3 calorimeters, and the fits to each of these give typically on the order of 3 to 5 picoseconds, and then when we do a combined fit, we get down to about 2.3 picoseconds of what we believe is sort of the intrinsic timing in this, of which the contribution for the oscilloscopes we used is a non-negligible fraction of this. Okay, so the question is, how do we exploit this kind of timing with a next generation of electronics? Well, one of the methods is what I'm going to talk about, which is what we developed in Hawaii for being able to measure these very high energy neutrino interactions in Antarctica. It was a real challenge. We needed to basically fly a 100-channel sampling oscilloscope, and it needed to be completely solar powered. So that was an interesting challenge. So we were very conscious of going solar power. But this same waveform sampling technology has been enabling for a number of detectors. And the place where I got most interested in this was about 10 years ago, which is when we developed a sampling chip here, which was running at about 2.6 gigasamples per second, and it worked just as well as our 2 gigasample per second tectonic scope at the time, but it was on the order of $10 a channel versus $1,000 a channel for the detector, and it was very low power and so forth. And so one of the things you notice with these chips is that, in fact, if you look on here, the chip is this little tiny thing here. Trying to get the signals in through all the cabling kills you. And so the cost in any of these systems is trying to reduce the packaging to be able to exploit the power of this. Okay, so what is this? Well, this waveform sampling is about the simplest possible technology you can imagine. It's essentially just a capacitor with a switch, right? So you go into tracking mode here. Whatever's happening in real time in your analog signal, you follow that, and then at some point you hold it, okay? Now, you can go and spend the next hour talking about these different details of how you do this, but this is, for the physicists in the room, this is the conceptual thing you keep in mind. It's a very simple process. You track, you store the sample, and then you decide later on. Most of the time you don't care what the sample was, but in this case you care, you digitize it, and you read it out. Okay. So how is this done in terms of implementation? Well, you can generate a very fast sampling speed by just these little boxes here represent individual delays. And by controlling those delays, you can control how fast the individual switches go into track and then hold mode. And because the stored capacitor out here can be very small, and you don't necessarily have to move the signal after, you can provide a buffered copy of it, to represent a change in voltage, for instance, is only about 100 electrons. So it's energetically extremely efficient. You spend most of your power just opening and closing a CMOS switch, which is also a very low-cost process. And so you can see here a very high frequency, 300 megahertz sine wave signal, for instance, of 50 millivolts input amplitude going into this thing. We end up resolving it quite nicely. Okay. So when you design such a structure, you have various choices to make. How many channels am I going to put in there? What's the storage depth of the channel? How am I going to do the timing control? What am I going to do for triggering? Am I going to do the analog-digital conversion on-chip or off-chip? And so forth. Those are important details and are very specific to each application. Okay, and I'll show you a very specific example of one that we've just are in the process of completing commissioning on, which is a device that we developed for the Bell 2 experiment for the Super V factory. So the idea here is that we have triggering on board. We have ping-pong sampling, so we're continuously writing from our sampling array into a much, much deeper storage array where we can keep out here almost 12 microseconds of storage depth. Okay? And then when we get a trigger, which comes 5 microseconds later, we select windows of potential interest based upon our trigger primitives, digitize those, and then send them out for feature extraction. Because we do the triggering, the ADC, and everything on multi-hip buffering and everything on die, it's very cheap, and the performance is quite good. As an example of the trade-off we decided to do in terms of the sampling speed, we basically get, for single photon detection using a microchannel plate PMT, we basically split the error, which is about 50 picosecond per phototube per PE, based upon the peak here, into about a third is due to the clock distribution system, which we could do better, but we didn't bother, just because you spend a lot of power and effort there at this point. The actual transit time spread of the photodetector itself, and then finally the electronics. The contribution from the waveform sampler is roughly equivalent. Now we know we can do better than that, and that's what I'll spend the next few slides talking about. Okay, so already towards the end of the last decade, we were doing a number of studies about what it would take to get to the single picosecond level. Now, at the time, people were sort of laughing at us, and actually it was difficult to get these journal articles published because no one believed we could get there at the time. We've subsequently done that, so I'll come back to that in a minute. But in fact, when you're at slightly above the 1 picosecond level, signal-to-noise ratio, as you might imagine, is very important. It's a very simple equation you can derive based upon sampling, where you see that the 1 over the signal-noise ratio is the linear term that comes in, and then you get 2 terms that goes 1 over the square root, 1 over the square root of the analog bandwidth, which is not surprising because it's the rise time of your signal, and then how fast you sample it. Okay, so you're only winning as the square root out here, where you're winning directly in 1 over signal-to-noise ratio in terms of doing these timing. Now, this equation does break down, and there's when you get about the picosecond level or below for reasons that have to do with the fact that to get this kind of bandwidth is actually quite a challenge, and you have to understand completely your system. Okay. So we made these predictions, like I said, towards the end of the last decade. We've subsequently done measurements with our more advanced chips. The picosecond 4, for instance, runs at up to 15 gigasamples per second. We can see that we can get down to the picosecond level, as can the DRS4 and some of the other advanced chips. But they suffer as you go through the delay chain in terms of errors that propagate. And so this is something that we have addressed and are working on for the next generation of such devices. But where this becomes interesting to other communities is once you start to get it down to the picosecond or below level, you're now at the place where your timing information is comparable to what you can get from, for instance, integrated semiconductor devices. And that's very interesting for people who are building next generation light sources and so forth, where you would like to have very, very precise space and time measurements at the same. So that's the real challenge here, is to try to do this. But I'll focus on just one aspect of that, which is that how do we take and actually implement this in a production chip that goes beyond the picosecond 4, which only has a very limited sampling array. Okay, so to do that, we studied. So the picosecond 4 was developed specifically for the large area photodetector collaboration project, which was trying to make very inexpensive microchannel plate tiles to give good single photon timing. We see that we get pretty good response here in terms of the analog bandwidth of these inputs of these devices, but it wasn't as good as we wanted. And we think we can get up to 3.6 gigahertz, and so we studied this quite intensively, as well as working on ways to reduce the calibration. So it's not terrible what you get for timing without calibration, but you do have to put in some effort to do that calibration to get down to, say, the 5 picosecond level. more recent chips, by fine-tuning, we can do in hardware the trimming down to the 1 to 2 picosecond level. And so that's really what the user wants. You don't want to have to do any of this calibration. You want to just turn it on, have it auto-calibrate, and give you very good timing. Okay. So what we found, and this is hardly surprising, is that with the choices that we made for the switches, we see that if we operate with a bias here at relatively low value with respect to our VDD over 2 point, we can easily get up to 8 gigahertz of analog bandwidth. That's not the problem. The problem we're running into is when the NMOS and PMOS are both not putting up their best fight in terms of conduction. Okay, you can see that in terms of a spike here in the resistivity. This does two nasty things if you operate around here. One is it lowers your bandwidth. The other is that it tends to distort your signal quite significantly. And so this is something that we've worked hard in the layout now to improve. And we think we can, we'll be able to do a much better job of this. Okay? So this is the current chip that we've designed. It's got a very long and somewhat, let's say, difficult to remember acronym, contorted at that level. So the prototype has 4. Okay, but the follow-on design for this is actually for a timing vertex detector, which would use time of flight, and we plan on 250 channels for that. Yeah. And that's the limit we could probably do with 130 nanometer. We could go to 65, but it's expensive, and we haven't decided that we want to do that yet. So we want to see how well we can do with this first. Because with the other design, we believe we can get to 200 femtoseconds. So we want to do that first, and then we'll decide in terms of this trade-off space. Because no one's in danger of building a detector based upon this technology tomorrow, but we are thinking ahead about what that might involve. So the example here shows 4 channels. So it's basically the same general architecture that I showed, maybe slightly modified in terms of where the blocks are. But you see there's a sampling array here up front, which has a primary input buffer. This is where you spend most of your power on the input if you use an input buffer. So that's something we're working hard to try to get rid of. And a much larger storage array. So the target specifications here, we decided to go with 4 channels for this one. 8 channels would probably be for the 65 nanometer node. And we're sampling at 10 gigasamples per second as our primary, 32,000 storage cells. So this gives us a few microseconds of buffer depth. We can extend this. It's just a question in principle of cost, although you have to play tricks then in terms of how you do the storage transfer so you don't burn an enormous amount of power. And you can see here, this is relatively high power right now, but we haven't really tried to do much to reduce that. We have some ideas on how to do that, but first we want to demonstrate that we can get reliably, without any intervention by the users, down below the 5 picosecond level for a very large storage array, and then we'll go step by step from that. So this is sort of our strategy for where we are right now. We believe we can get the few picosecond level in the short term, and then longer term we're going below a picosecond. Okay. All right. So in summary, I would say that I used a somewhat contrived example here of a detector based upon Cherenkov radio emission for calorimetry. This might be pretty interesting in the future. We'll have to see. I mean, what's nice about it, as I showed, is it's extremely radiation hard. If we can somehow get the threshold down into a reasonable level, then it might be an interesting, very forward calorimeter technology. Or a timing detector for something like the FCC-HH. We believe that if you can build a large extended structure, we'll have single picosecond type timing resolution. We don't think that there's there's anything harder out there in terms of radiation hardness, so that's very intriguing. And then for these next generation of waveform samplers, we believe that we can match the timing resolution at the picosecond level, and that we can do this with very dense arrays of channels, which becomes attractive if you can manage if you can manage it thermally. So that's all I was going to say for today. Thank you.
Sampling at high frequency always have a fun, including saving some time.
Yes.
Fantastic. So question, please.
I mean, maybe you are aware, but Dominique Breton from Paris, he did. Yes. I mean, this kind also of waveform, and he reached it down to
right. So we just actually saw him at Torino the week before last. Yeah. So we've known each other for a long time. The primary difference in in this architecture, which is where we've gone this different, is we add the storage depth here.
Yeah,
So,
okay.
so
This is
this you have to do if you're doing a radio signal because we just don't have, it's not like a single photon or a shower where you can say, okay, this is what I have to read out. We have to go do post-processing on this to really get it fully.
I agree.
To my
Yeah.
knowledge, you have this chip, you have Dominic Breton, and you have Stefan Rett.
Yeah.
Right. Which they're working on the fifth generation, the DRS5, which is more like the SAMPIC, for instance, which it selects very narrow slices in time, and that's a very common. And we decided to go a different route for this because we know for our radio work, for instance, we have signal noise ratio of 1 on our antennas, but when you phase them up, you can get to signal noise ratio of 10. Okay.
Just because I am very interested by this, what is the maximum number of channels we can put in your ASIC? Can we go to 1024, or it's forbidden?
It depends on how deep you want to go in the sample. It's all a question of sampling depth. Yeah, it's all a question of sampling depth. So I can't tell any about the details, but we've already designed chips that are intended for this type of application, where you have a very pixelated array of these devices, where people want to be able to maintain, a few picosecond timing. They don't have to wait for long periods of time because their events don't last very long, but they need to know everything during that 100 nanoseconds or something.
Okay,
Yeah.
thank you.
How big is the chip?
Which one?
The one you
So this one, I thought I had
one is-
the prototype here is about 5 by 5. Okay. Typically, our bigger chips, what earlier one I showed is more like 1 centimeter by 1 centimeter. Okay. That goes with the technology. If we go, eventually, because this is so dense, especially the digital part of it. So one of the things that we changed in the earlier chips, everything was done with FPGAs that were adjacent to them. And that created all kinds of problems, not the least of which is you just can't meet timing on a lot of these things. So we had to move all the timing and control inside the ASIC in order for this. And once you do that, then it's very simple. You just have a high-speed, like that was shown in much of the chips earlier, a high-speed link that allows you then to calibrate, do everything you want to do, configure things, and read out.
Thanks. One final question.
Thank you. Actually, just two very short ones. When you talk about radiation hardness, what are the doses? I mean, in comparison with the CVD, I mean, can you just quantify that?
Well, you mean in terms of what part of it? For the Illumina itself, that's published data. I don't happen to know the number off my hand, but pick your favorite, reactor, and chances are part of the structure that it is Illumina. Okay, it's extremely hard.
Okay, and the second question is, what are the dimensions of the structure that you showed at one of the first slides? I don't remember anymore.
Let me, you mean in terms of that? So what we've done here was we chose a size that was convenient in terms of waveguides that we could easily couple existing low noise amplifier feed horn arrays to. We would probably go to, I forget the exact WR number, but we would go to a much higher frequency device for if we're building a full calorimeter. Okay, but that's a choice. I mean, if you go to your favorite microwave textbook, you'll see there's all sizes, and we can cut the Illumina to whatever you want, and the same principle holds. Okay.
Okay. Thanks. One final advice: don't go to Antarctica with your fantastic Hawaiian shirt.
Oh, I've been there many times, actually. Everyone McMurdo, which is where we launched from, is the Waikiki of Antarctica.
Okay. So the session is over. Thanks, everybody.